Okay, so here is a drawing of the problem described in the exam with water on this side of the barrier from 0 to 5 centimeters and D2O on this side of the barrier from 5 to 10 centimeters. Question 1 asks for the overall mass flux, which is equal to the total mass concentration times the mass average velocity. I'm going to start by first finding the total mass concentration. Total mass concentration is equal to the sum of the component's mass concentrations, which can be found by dividing the mass of the component by the total volume, that formula right there. This can be further broken down into the density of the component times its individual volume all over the total volume. The total volume is equal to the sum of the components' volumes. Since both water and the D2O fill up the capillary tube at a length of 5 centimeters each, their volumes are equal, which means that each component's volume is equal to half of the total volume. Plugging that simplification into the above equation for each component's mass concentration and plugging in our known values, with these canceling out because you have the total volume, we find that the mass concentration of water is 500 and the mass concentration of the D2O component is 555. Then the total mass concentration is equal to the sum of those two, and we get 1,055 kilograms meters cubed as our total mass concentration. Now that we have the total mass concentration, which is this right here, we need to find the mass average velocity for the system. Starting off, we know the sum of the molar diffusive fluxes must equal 0, as stated in the textbook. So the molar diffusive flux for a binary system, the diffusive fluxes are going to be equal to each other but in opposite directions. In this case, the water is positive 2.78 as given in the problem, and D2O is negative 2.78. Next, we take the equation for a component's molar diffusive flux, which is equal to its molar concentration times its individual velocity. Unfortunately, we do not know the individual concentrations for our components, but we do know that concentration, this can be broken down into this formula, which is equal to the moles of the component over the total volume. Again, we don't know the moles of the component, but it can be further broken down into the mass of the component over its molecular weight. So going ahead and subbing these all into each other, we get this formula right here. And we find, plugging all of those things in, we find that the velocity of the water component is 1.0008 times 10 to the negative 4th meters per second. And again, doing that for the D2O, using this edited formula, we find that the velocity of the D2O component is negative 1.0018 times 10 to the negative 4th meters per second. That negative sign makes sense because the D2O is moving in this direction in the capillary tube while the water is moving in this direction. That's considered the positive Z, and this is considered the negative Z direction. Next, we need to find the mass average velocity of the system using what we just found. We know that the formula for the mass average velocity is equal to the sum of the mass fraction of the component times the component's velocity. So for this binary system, we have water on one side and D2O being added to that. We can further break down the formula for the mass fraction into the individual mass concentration over the total mass concentration, both of which we know, so we're just going to go ahead and sub that in. And we find that the mass average velocity is going to be negative 5.271 times 10 to the negative 6 meters per second. And that's just using those values that we had before plugged in to this, again, edited formula. Finally, we can find the overall mass flux by taking the total mass concentration that we found above and the mass average velocity that we also found above, and just multiplying those by each other, and we get the overall mass flux corresponding to the maximum molar diffusion flux is negative 5.56 times 10 to the negative third kilograms over meters squared seconds. So that is problem 1. So for problem 2, I'm going to start off by stating some known equations or assumptions that we can make. First, as stated in the book and said above, the sum of the molar diffusion fluxes is going to equal 0. From that, we can say that for a binary system such as this one, the sum of the two molar diffusive fluxes is 0. And we can rearrange that equation. We can say that the molar diffusive flux of component 2 is equal to the negative molar diffusive flux of component 1. Another assumption we can state is that the sum of the mass fractions is going to be 1. So for a binary system such as this one, the mass x1 plus x2 is going to be 1. So again, rearranging that, x2 is equal to 1 minus x1. Next, we're going to look at the formula for driving force for diffusion, which is equal to the change in x with respect to z, equaling the sum of x1j minus xj over the total concentration times the Stefan-Maxwell diffusivity ij pair. Expanding this formula out for our binary system, we get this equation, and we get this term to cancel out. And using the statements we made up here, we can go ahead and plug those in and make the equation only in terms of J1 and X1. Expanding out this numerator here, foiling it out, we get this, and again, we have terms canceling, and so then we are left with this equation. One other assumption we can make, since this is almost perfectly ideal solution, the Stefan-Maxwell diffusivity 1-2 pair is equal to the diffusion coefficient of components 1 and 2. So that was there, but we can go ahead and sub that in. So subbing that in and removing out canceled terms, we are left with this equation. Now we can just plug in our known values, including concentration, which we found in problem 1. We get a driving force of negative 5.007 times 10 to the fourth. So the order of magnitude estimate for the maximum driving force for diffusion at t equals 0.1 seconds is 10 to the fourth. Next, we're going to look at the graphs. For density, we know that, I'm going to go ahead and switch my pen color really quick so it stands out a little bit more. For the density graph, we know, or the mass concentration, we know that at the beginning there's that barrier right down the center. So the water component is going to be completely on the 0 to 5 centimeter side, and the D2O is going to be on the 5 to 10 centimeter side. At t equals 60 seconds, it's going to start blending a little bit more. There's not going to be that harsh division between where the water component stops and where the D2O component stops, which accounts for the not as steep slope of the components. And then the final, at t equals infinity seconds, there is water throughout the entire capillary tube, and there is D2O throughout the entire capillary tube. The same can be said for the molar concentration, or the concentration of the system. Again, the water component is going to be entirely on the 0 to 5 centimeter side of the tube, and the D2O is going to be on the 5 to 10 centimeter side. As time progresses and we're at t equals 60 seconds, they are starting to diffuse onto either side, and so you have a little bit of the D2O on this side and a little bit of H2O on this side. T equals infinity seconds, the system has reached equilibrium, so there is equal amounts of D2O and H2O throughout the entire capillary tube. Next, looking at the molar diffusive flux components, we know that at 0.1 seconds, the maximum molar diffusive flux is reached, and that is the 2.78 as given in the problem statement. At 0.1 seconds, there has not been much diffusion occurring because you just removed the barrier and they're just beginning to be flux, but you're going to reach that peak for both, for the water component we know that the water component is the positive one because it is moving in the positive z direction, and since, again, as we stated above, the sum of the molar diffusive fluxes has to be 0, so the D2O component is going to be negative 2.78 to match that of water. Now, this is a very steep slope because the water component nor the D2O component has had very much time to diffuse onto either side of the capillary tube, so it's only covering this very small segment in the tube where there's diffusion occurring. At t equals 60 seconds, a little bit more diffusion has occurred, and we're getting the water to move and the D2O to move, so we're having those slopes kind of relax and they're not as steep because it's starting to diffuse throughout the entire tube. And then again, at t equals infinity seconds, the system is at equilibrium, so there is no flux. This is at 0. There's no molar diffusive flux because it's all completely spread throughout the entire tube. Finally, looking at the mass flux, overall mass flux graph, we know, similar to this graph, the flux is only occurring in this small segment in the tube because at t equals 0.1 seconds, there has not been enough time for diffusion to happen throughout the entire tube yet. So that's where there is such a steep slope here. And it reaches that negative 0.5 that we found in question number 1. So that's where that peak occurs. And then at t equals 60 seconds, similar again to this one, that flux is starting to spread throughout the entire tube, so that slope is not as steep. And then at t equals infinity seconds, the capillary tube is at equilibrium and there is no flux occurring. So I'm going to go ahead and erase all these little marks I made while I was talking so that you can look at my graphs all together.